Hi, thanks everyone for joining the third tutorial. So in terms of the time I spent for this tutorial, it's like way more than the previous two tutorials combined. So this topic is the satellite shield. So the first thing I want to explain is like why it's called a shield, and it's just the PCB board why it's called a shield. So if you search shield, like either in Arduino official website or SparkFun, you see a lot of things like that. And for example, here, so this is a board for Uno. It has two rows of pins here, and the shield also has two rows of pins that's like designed to match the two rows on Arduino. And when you insert it on the top, it's like a shield covered on top of this board. Although later, a shield doesn't necessarily look like a shield. Maybe it's just some peripheral board, or for Teensy, like Teensy has very small circuit board. So the shield sometimes is like attached from the bottom or not onto the Teensy at all, but the name just remains as a shield. So let's look at these shields, what they are doing. So for example, this shield is called a 4 relays shield. So basically, you can use the signals from the individual digital pins to control the opening and closing of some external circuit, and usually those circuits pass this very big current, and it's usually used for, like, for example, driving motors, driving solenoids, and those kind of power hungry devices. And and you can already see in neuroscience we will need something like this very often. And also we have this kind of shield, and this is a Wi-Fi shield. It just provides the Arduino board the access to some wireless chips here, and giving it wireless communication capabilities. And so this one is an XBee shield. It's just similar to the Wi-Fi shield, but just using a different wireless communication protocol. And this shield, so it's called a SparkFun MIDI shield. It allows you to build some MIDI devices to like play music and stuff. But essentially, it just has a lot of knobs and buttons. And you can, and actually there are versions where the buttons are not like these kind of physical buttons, but like kind of touch buttons. And then you can relate this to the neuroscience behavioral control applications, where we need to detect lever pressing, which is often a mouse or a rat like pressing a kind of mechanical button, not exactly like this, but like something suitable for them to press. Or we have like contact detection, for example, like paw touching somewhere or licking. Those are all touch contact detections, and there are versions of shield that actually does contact detection. And we even have this kind of shield. There's no components on it. It's a breadboard for prototyping, and just like certain holes are connected to certain pins that allows you to do the prototyping a little bit more easier and more integrated than having a separate breadboard. The example I was showing here is the Teensy audio shield, and this will be one of the topics for next tutorial, which allows Teensy to have full control and very powerful control of audio generation and playback monitoring and the feedback control, and a lot of fancy stuff over there. And it's obvious why I was talking about these particular shields. It's because these are the most relevant. So this shield provides the most relevant functions for our day-to-day behavioral experiments. But here we have 1, 2, 3, 4, about like five kind of external circuits, and then those are kind of bulky, and then many of them have to be connected to a specific kind of board in a specific kind of way, and one at a time. So that's why I thought why don't we just put all the capabilities in one single board and then match it not with Arduino Uno because it's too lame, too slow, but with Teensy, which is one of the fastest and powerful microcontrollers. So here, this is the satellite shield. Let's begin with the simplest. So you see here we have a Teensy 3.2 board. So like here are two rows, the inner two rows, and the number of pins in the inner two rows matches exactly to the two rows for Teensy. So this is important. Like don't shift this one up or one down, because then you are risking burning the Arduino board. And thanks to the consistency of the pinout of different Teensy versions, that was of course includes a 3.2, 3.5, 3.6, 4. The fourth generation, and so the initial part of the pinout of the two boards are exactly the same, or in terms of our satellite shield, they're exactly the same. And that's why we're gonna connect the USB end still at the end of these two rows, and then press it down. Yeah, so for later demonstration, we'll just use this, but there's absolutely no difference between using this or that. Yeah, so the first thing you can see is that we directly have a breakout for this Arduino board. Pinout is basically providing access to these individual pins, and so I'll put it in a vertical direction. These pins are connected to their respective rows of sockets, and over there and to the respective row of socket. But important thing is you see kind of tiny labels on some of the pins. Let me put it more closely to the camera. Maybe it's easier to see. So here, the pin number 2 has the asterisk, so it looks like a white dot, but it's actually asterisk next to it, and 3, 4, 5. And so for these pins, oh, and also on the other side, we have 23rd, 22nd, all the way to 19th pin labeled with asterisk. So for these rows, the inner row and the inner pin and the outer pin are not connected. And if you want to connect them, you have to use a jumper to cross the two. So, but for the and also like here we have 2 pins labeled L1 and L2, and those are also not connected. But for all the other pins that are not labeled with anything, the inner row and outer rows are connected. But that sounds complicated, but one thing you can be sure about is like the inner row of the two sides connects to the pin directly for all of them. We have power buses, just like the red and blue lines on the side. So you can find 2 power buses. One is on the side here. You see here is labeled 5 volt, here is labeled ground, which means the top rows here are looking from the current view, the top row here, or in terms of the board, the inner row here are 5 volt, and then here are for ground. Same on the other side, so 5 volt and ground. Okay, so here, so we had the breakout, but also, previously I showed you with a shield that doesn't have any component, but just a bunch of holes, which is a breadboard. And here we have a little area here that serves as a kind of on-site breadboard where you can, for example, build some custom circuits, like can be a simple voltage divider, or can be an operational amplifier, and you can wire it as a buffer to or to amplify your incoming analog signal. So And here on the side, and we see like 2 rows here, and 2 rows are labeled with a white line on the side, and that indicates like these 2 rows are connected. And over here also these rows are connected. But the holes in the middle are all isolated from each other, so there's no like horizontal or vertical connections inside. They're all isolated holes. Okay, so we talked about the relays, and then where's the relay portion in the satellite strip? So that's basically over here. Okay, so this is a block terminal with 10 pins, and 10 pins means 5 pairs. So like this is 1 pair, and this is 2nd, 3rd, 4th pair, and the 5th pair. So basically this block terminal provides 5 channels of high current output. And on the other side, we have another 10-pin block terminal that provides 5 pairs of high power output. And of course, high power output have high current and sometimes high voltage. Then here we have sockets that provide external power supply. I will get into more details later. Here we have the connectors for contact detection, which is here in this block terminal, L1 and L2. And here we have a port called a VB plus, means the plus terminal of the battery power supply. And basically this conductive contact detection circuit detects whether there's current flowing out from the battery's side and flowing into the L0 and L1. So when there's no contact, the circuit is open, so then there won't be any current flowing into that. There's no signal. But when there's a contact, the circuit closes, and you have the contact signal. Okay. Now I'm going to talk about the wireless modules. So there's no wireless chips on this board, but it provides interfaces that allows you to connect standardized and popular wireless modules. So the first one is this. So this is a ESP8266, a super popular, cheap, low power, mediocre performance, but that's a trade-off. Wi-Fi module. So this is a socket for the module, and we basically connect it like this. And this module communicates with Teensy through serial port 1. Serial port 1 here. Yeah, RX1, RT1, so which is port 0 and port 1. And that interfacing is not going to affect any functionalities about the driver output or contact detection, because the 0 and 1 are here. They're not accessed to any periphery. So, but it's labeled here RX1 port 1. And alternatively, so you can connect a XBee module. So this is XBee module. So on the top is the XBee module, and here is the adapter, it's a serial adapter. And then so the adapter gives you 6 pins, but here we have a 6-pin socket which connects to the middle 6 pins. And here you go. That's basically the overview of the satellite board. Next, we'll focus on the driver circuits. Why do we need these driver circuits? Well, because the output of the microcontrollers are very weak. And just to put some numbers on it, we can, for example, go to Arduino Uno's web page and navigate it to the tech specs tab. And here you can see like DC current per I/O pin is only 20 milliamperes. And then is Teensy better? Actually, no. Teensy is worse in that respect. So if we look at like from Teensy 3.2 all the way to the latest version, Breadboard I/O current output, and so they're all like 10 milliamperes. But they actually don't need to be high. So first, they just simply cannot be too high due to the limitation. And second, they don't need to be too high because they are intended to be used as control signals. Yeah, but when it comes to the mechanisms of how this kind of control works, imagine a presynaptic neuron is trying to activate the postsynaptic neuron. The neuron has a way to amplify that signal. But in this particular case, we have a small current gated by the presence of glutamate, and that small current causes changes in intracellular voltage. And then once the intracellular voltage passes the minus 40 millivolt threshold, then the voltage gated sodium channels will be activated, and those channels are like super abundant and powerful. So then all of a sudden we got a big action potential. So that is basically the idea of amplification. And the mechanism of amplification in electronics is actually conceptually the same. So for example, for the circuit in the satellite field, I used the Darlington transistors to amplify the small signals, or actually you can say like to use the small signal to gate the big current. Here, the big current eventually will flow from the C and along this line and to E. And B is where our small control signal is being applied. So when a small current going through here, going into B, of course the current has to have somewhere to go, which is along this line. And just like the amper receptor opening is still gonna putting charges into the same soma that the sodium channel opening does. So, but this is a small signal. The small current goes into that, goes into here, but going into here will cause a lot bigger currents passing from this branch over here to here. Yeah, it's about 50 times the current than the control current. And then that will flow into another channel here. And then this current will allow another way bigger current to pass through. So this is already different from what I was talking about. Like here, like my analogy only involves one level of amplification, but here and we see like two levels of amplification. So here I've already uploaded a program in here. So the program is very simple. I'm just turning the 19th pin on and off, like 1 second on and 1 second off. And then we can try to hook up an LED to this 19th pin. So on one side, I'm going into the inner row of the 19th pin because that directly accesses the pin on the Teensy. The other one goes to the ground. And you see this is going on and off 1 second at a time. Okay, nothing special, but here, let's use this. So what is this? So this is the vibration motor, which you can find in some old phones. Inside it is just a DC motor. Its center of gravity off center from this disc. So when it's spinning, and it's kind of shaking this around. Okay, so question, anyone? So what's gonna happen here?
It'll be vibration.
Nothing.
Right?
Okay, so great. We have two answers. So Will said nothing, and Isa said there will be vibrations. So okay, so I will buy a beer or coffee for whoever answered the question correctly. All right, moment of truth. Wait. Okay, so yeah, something wrong. Okay. Well, okay, so this is certainly not what I tested. Okay, so what's going on here?
I win.
It was ISIS's destiny to get that free beer from you.
Yeah, well,
The gods have intervened.
yeah. Well, okay. This is a failed demonstration. I think this motor has a rated current of like 30 milliamps. The minimal current is 30 milliamps, but the board is supposed to only output 10 milliamps. So I didn't know. Maybe this is a different kind of motor that I picked. Okay. Well, okay. So, but I'll proceed. I'll proceed with. So Isis was right, but maybe here we can just observe more carefully. I'm just to try to save the situation. So carefully about the intensity of this vibration. Yeah, so the intensity is something like this. I don't think it's reaching the full intensity that this motor can do. Now, let's connect the pin to the driver circuit. Basically, we are connecting the 19th pin to, like the base or the control point in the diagram I just showed you of the Darlington transistor. And doing that requires to use a kind of little jumper. Yeah, building this is easier. It's easy. So we have this kind of double-sided male pins. So one side is longer, one side is shorter, but it doesn't really matter. And here we have the female jumpers, and we just put it on one side, and then that connects the two pins together electrically. And then, so I'm inserting it into the 19th pin, bridging the inner and outer row. And on the other side, oh, actually, I will plug it in later, so so that I have some time to get this hooked up. Here we have 19 to 23, so this number matches the numbers labeled on those pins. So basically, I will connect the minus lead to the minus sign to the socket 19. Just lightly tightening it is fine. And a plus sign to the plus pin. Now vibrating, because we need to connect it. Yeah, so this is a lot more vigorous than before. And the reason it's being more vigorous are twofold. So first of all, okay, so I'll hold it in my hand so it doesn't make as much noise as it. So our twofold. The first is, of course, the current supplied by the board is only 10 milliamperes, which seems to be enough to drive it to make some vibrations. But the output from this 19th pin is up to 500 milliamperes, but of course it's not outputting 500 milliamp, but that's the maximum of its capability. And for many other pins, they supply 1 ampere of voltage. And the second reason is the board only outputs 3.3 volts, but currently the default voltage for this driver, for the output of the Darlington transistors, is 5 volts. So then this vibrator is receiving higher voltage, and also is being supplied with an abundant current. And of course,
Hey Manny,
yeah.
Hey Manny, can I ask a question? So
Yes,
why does
please.
that amplification happen when the sort of the green gates that you plugged into between the Teensy board and the green outputs? Like, where does that amplification of that current happen?
Oh, so it happens in the Darlington transistors, and the Darlington transistors are these. So this,
I see. Okay.
This IC and that IC. So this IC controls is associated with this terminal block, and that IC for that block.
Gotcha. Thanks.
So the outside of the, oh, you can actually see a little bit of traces on the board here. You see? Yeah, so the output of the 19 pin goes here and to this side of the leads, I think, and then that goes into this IC and gates the current pathing through the other side of the lead, and which is of course connected to the board. Yeah, I'm glad Rajan is bringing our attention to here because my annotation may at the first glance look a little weird. The numbers of the Arduino pins are actually labeled on the negative side, negative terminal, and there is not arbitrary. There's a reason, actually an important reason for this. Just imagine we have I know this is LED, but just imagine this is a light bulb. At the bottom, you're gonna hook up a battery, so the battery will power the light bulb. It will turn the light bulb on, right? Because the current is flowing through it. And then, let's imagine this is no longer a resistor, but a switch. But there are actually two ways to set up the switch. So you can switch at the positive side, or you can switch at the negative side. And then, but for a transistor, okay, actually this is a good example because this is a diode. It only allows the current to flow one way, but not the other. So that will create some problems. So the problem is when the switch is open, and you try to measure what's the voltage across the two, and of course the potential of this is the potential of the one side of the battery. But when you measure here, this potential is called floating. It's not determined. It's arbitrary. It's actually influenced by the electromagnetic interference in the air. So then if you hook up a oscilloscope and you just see the voltage going up and down, drifting to nowhere. Or maybe it has a specific value, but we don't know why that specific value. So basically that's a floating terminal. So here, the reason we have the number at the minus sign means that the switches or the Darlington transistors is controlling the opening and closing of the minus sign. Plus sign is basically a constant high voltage supply. So if we use a 5 volt, these pluses will always be 5 volt. And only the return current get open and closed, controlled by the Arduino pins. That has two implications. The first is you have to be careful about interacting with these plus terminals, because if you hook up a wire here, so let me just demonstrate using a jumper wire here. So if you hook up a wire here to the plus sign, and then we are just dangling the free ends to here and there, and if the free end like scratches the circuit board, now who knows where this is going to touch. And with such a high voltage, it's very easy just to cause a kind of massive damage to the circuit. So this is different from having the switches on the plus sign, because in that case, assuming like the switch is usually open, so then the lead coming out of there won't cause any damage to the board. So yeah, this is the first implication. So the second implication is that in experiments, we not only want to output some powers to the peripheries, but we often want to record what we do about the peripheries. For example, like you guys use the piezo to vibrate the whiskers, but you also want to like record the signal you send out to vibrate the whiskers and back to an analog input channel. And you cannot do it here, because when the output is activated, yeah, of course, the minus goes to ground, and then the plus goes to the high voltage of the power supply. But when the transistor is closed, so you get the power voltage from here, from the plus, but the minus is floating because it's the transistor circuit, and you won't get anything useful out of that. So this is an actual mistake a previous user has bumped into, and then I think it's important to make that clear. And now the question is, then how do I get that that signal? Because that is important to record sometimes. And the answer is we just split the signal from the side of the pin rather than here, because the pin reliably tells you like whether it is a high or it is a low. But you may say like, oh, I have like bridged the two, then where can I kind of tap into this, kind of bridge the signal? It's actually pretty easy. So so here we have this jumper, and we just move it this way. Yeah, the bottom part is still bridging the inner and outer row, but we have a little leads like exposed on the top, so you can basically solder a wire from the top. Then that's in that way you can split the signal. Oh yeah, by the way, of course. So you split that signal, that's one lead, and you also need to tap into the ground to have the reference. So we have in total 10 channels of power output. 4 of the 10 channels has a current limit from the block terminals of 500 milliamperes, and then the rest 6 channels can provide up to 1 ampere. So the channel 2, 6, 19, 23 are 500 milliamperes. Others are 1. And so oftentimes we need to interface with peripheries with different power. For example, this vibration motor is 5 volt, and in the lab we have, for example, 2 kinds of solenoid valves. So one is a 5 volt valve, and another is 12 volt valve. So, which means we often need like different output voltages. So this board actually allows you to use 3 different kind of voltages. So one is 5 volt, and the 5 volt can be conveniently supplied basically by the USB, and once you plug it in, so the circuit here actually will bring the LED, not LED, the USB 5 volt supply to this power buses. Moreover, it will bring it to the 5 volt to the 5 volt pins over here. So what are these for? So these are for selecting which power do we want to supply to this Darlington transistor array, and which controls which delivers the power here. And this jumper selects the power to this Darlington transistor array, and which supplies the power to these terminals. VD1 means a voltage for the driver 1, so which is this driver. And then 5 volt is typically from USB. And the VS1, voltage source 1, is an alternative voltage source that we can supply into here, VS1 ground. And then let's say we are supplying a 12 volt to VS1 and ground. And then this pin here will have 12 volt. And if we connect the jumper across the VS1 and the VB1, so then we are now supplying 12 volt to the driver. And of course, previously I kept it at the other side, so now we are supplying the voltage driver 1 with 5 volt. And the same for the other side, so except here we have VB2, and we are selecting between VB2 and the 5 volt for this driver. And the VS2, voltage source 2, is supplied via these 2 sockets. But you can also see that here we have a 5 volt socket. That's because like the typical USB 2.0 or something can only deliver up to 500 milliamperes of power, and for 3.0 and maybe later, I think it can deliver up to 1 amp, a little more. But imagine if we are connecting like a lot of motors, and then which may be drawing a lot of power, the USB power may not be sufficient. So in that case, we can hook up additional power supply to the 5V to supplement the needed current. And this supply will be combined together with the USB supply. And here is the sort of a caveat, is that if the two voltage source, the 5V sources, like one is a computer, one is another external source, are hooked up to different building grounds, then there might be a difference between the two grounds. And if that is the case, then you will have a constant current flow from one 5V to another 5V, and which may be causing problems. Maybe your external power supply is dumping current into your computer, and or computer back to your power supply. So that cause problem. So a recommended power source will be a power supply boxes. It's kind of pretty heavy one. So the output of those boxes are usually electrically isolated and kind of safe to be combined with other things. Cool. So let's move on to the next section, which is the conductive contact detection circuit. So first of all, I will explain what is the mechanism for this circuit. Okay. So this is, I think, one of the earliest reference I can find for the kind of leak detection. Let's look at this. Like, aren't they look very familiar? They should, because this structure, it just ignore the kind of resistors and a few additional wires. This is basically a cascade of signal amplification, very similar to what we saw for the Darlington transistor. Here, like, we are using the current that flowing through the subject, which is very, very tiny. And if I remember correctly, last time I measured it, it was at the microampere level. And it's such a small current, and you turn it many times, 1,000 times bigger, to a current that can drive a reliable signal that we can register. And of course, that signal is represented by the current flowing through the C and E. But of course, first we need to ensure like the current passing through the animal is extremely small. So here we are supplying the animal with the positive voltage, and then the chamber floor or the animal's body with another voltage. And when the animal touches the side, either using paw or licking it, the current will flow through that. But to minimize the current flowing through this circuit, then we need R1 and R2 to be very, very big. And in this case, it uses a 10 mega ohm resistor for R1 and R2. Then you can imagine like the animal, a dry animal or a dry knee, it's about like a 10 to 20 mega ohms. So if we have a 9V here, so after some divisions, so then we can have like some 2V or something over here, or sometimes even less. But that voltage is sufficient to activate this transistor, and then there will be some current flowing through it. And here we need another resistor that forms a voltage divider with this transistor. So here at this point, you can see this transistor as a resistor with a kind of changeable voltage. And when there's signal coming in, the voltage of the effective resistance of this transistor decreases a lot, while this resistor has a constant resistance. So that like the decrease of this will drive up the voltage at this point. And once the voltage here becomes high, and then the current will flow into the base, which drives a large current flowing from C to E. In this paper, they use the solenoid to open and close external switch. And the open and closing of that switch will give us the leaking signals. And then moving to the Genelia Ligand detector, and it looks way more complicated, but the bottom half of this diagram is irrelevant, because that has something to do with like RJ45 connections that interfaces with B control. And on the top, the left half and the right half are exactly the same, because they basically duplicated the circuit to have a 2-channel leak detection. And so which means like it's really just here. And here you see this very familiar components, which is a transistor, and here's another transistor, and here's a lake, 10 mega ohm, two 10 mega ohm resistors, and making sure only small current goes through that, and then the current passing through that will activate the current passing through that, will activate the current passing through this, which is the last one. And the current passing through the last step of the cascade can drive an illumination of an LED. And by reading out the light emitted from an LED, so we can get whether the contact happens or not from the other side. So here is a diagram of the circuits in this board. So this is the circuit of the entire board, but the leak detection part is only here. And then here we basically also have two channels, and the bottom is just a duplication of what's on the top. And so the leaking happens here, and instead of two bipolar transistors, here I just have a single MOSFET, a very high gain transistor, and then that will the opening of this transistor will cause current flowing through this vertical trace, and will activate the LED, and the rest is pretty similar to the Geneva one. So one special thing about the Geneva circuit is that it has a potentiometer here for a trimmer. This potentiometer together with this transistor together forms some effective resistance, and on the top is a 100 kilo ohm resistance. So the two sides of this node basically forms a voltage divider circuit, and then like push and pull the voltage at this point. But by changing this adjustable resistor, you can change the weight of this side, which biases how much to pull and push the voltage. And once you have that ability, then you can adjust the sensitivity of this circuit. For example, in the winter, increase the sensitivity a bit. And in the summer, weather is humid, conduction is easier, you may want to decrease the sensitivity. Yeah, so that's also different. But here I don't have that potentiometer. Yeah, so I have previously built some circuits over here. So this is the Geneva leak detection circuit, and then I'm just tapping into the power from the Teensy board for convenience. So it's supplied instead of 9 volt, it's supplied by 5 volt, and then the ground powered up is like the chamber in the mouse tube, and this is like the leak port, which is the other side. Yeah, and this one is a potentiometer, which you can adjust the sensitivity. I'm showing this is really just to give a very intuitive impression about what's really going on in the Geneva detection circuit. So, and this is just very quickly, this is my circuits, and then, oh yeah. There is have to confess that there is a problem with this, which is the high sensitivity is a double-edged sword, and the sensitivity is very high, but which means it's kind of prone to noise. Like if your wire connecting to here is very long, then it may pick up too much electromagnetic interference into that, and will cause some parasitic activations of the leak detection. Let's just quickly talk about the connections. So we are familiar with how to kind of bridge the inside row and outside row for those drivers, and the idea is exactly the same for the leak detection circuit, except that here the position dedicated to contact detection is the L0 and L1 here. We can bridge that like this way. And over here, I have explained in the very beginning that we have two channels, L0 and L1, but we just connect the animal usually, or the subject, to the high battery voltage, and then the buttons or contact points we want to detect to the L0 or L1. So why like all these designs require a battery? This is actually an important concept for folks who want to do electrophysiology. And the concept is called galvanic isolation. So galvanic isolation is what we do when we don't want the two circuits to crosstalk electrically. Why we don't want that? So here you see a little switch being opened and closed. So this is like a mouse licking a lick port. And on the other side, let's say this is the circuit. Well, this here shows this is signal detection circuit, but usually the signal detection circuit shares the same ground, or for example, the building ground, with the electrophysiology system. If this circuit on the left and right shares the same ground, which means we need to kind of draw a line down here to connect the two. Yeah, and also there's some lines over here is also connected. So then what are the lines? That line is from the mouse's body to the ground wire of the recording system. So then we not only have this loop and that loop separately, we have a middle loop. To break this middle loop, so we have to get rid of the common ground of the two circuits. If we break this loop, if we have this loop, then there will be current flowing through this loop, unless the potential of the two are exactly the same, which is impossible, because we are using a 9 volt or at least a 5 volt to supply the leak detection circuit, and the dynamic range for any electrophysiology system is unlikely to exceed, let's say, 50 millivolt. And usually the working resolution, the working dynamic range is plus minus 10 millivolt or even smaller. And then, like any connection coming from this, so if there's no galvanic isolation, any current coming from or any contact coming from this side to that side will have like 1 volt or like at least hundreds of millivolts, like pouring current down into the electrophysiology system, and then you just like immediately see a saturation of the recording. So, and this is what this diagram is doing. The two systems is communicating with each other through light. Switch closes here, the LED is lit up, just like how we demonstrated using the little circuits on the solderless breadboard. It's lit up, and on the other side is we have a photo transistor, and the light signal is converted to the change of effective resistance, and which changes the current flowing this side, and the current flowing this side will be converted to some like other kind of signals that eventually be registered by Teensy or by the control system or computer. So, and the components in this case here is called a photo isolator. And the photo isolators is located here. When you supply the board with batteries here, so you are basically supplying a separate circuit in this satellite board. So the battery circuits and all the other kind of voltage source, 1, 2, 5 volt ground, they don't talk with each other electrically. And the only point of communication is in this photo isolator through light. But of course, for example, Rajan has been doing imaging mostly, and Rajan really didn't care about those kind of, whether it's crosstalk or anything. So then if Rajan want to use that, Rajan can use a jumper wire to go from 5 volt to VB plus, and then to connect any one of the ground to VB minus. And then basically it's no longer isolated, but it's just a way to provide a power supply to the contact detection. Although I mentioned this circuit has a very high sensitivity and then it's kind of prone to interference, but it actually has a kind of post hoc way to eliminate some of them, so which is done by an LC circuit after the amplification. So the LC circuit after the photo isolator has already carried the amplified signal from one side already to another. So RC circuit has capacitors and resistors. Here we have two trimmers or potentiometers. Changing the resistance of the potentiometer, we can change the strength of this temporal filter. So then that presumably can get rid of a lot of kind of transient spikes that's due to loose connections and others. To put some numbers to it, we in the RC circuit, and like this. So we have a RC time constant. The tau equals the resistance times the capacitance. And here we have the trimmer can go from 0 to 100 kilo ohm, and the capacitors are fixed at 0.1 microfarad. So 100 kilo ohm times 0.1 microfarad equals 10 milliseconds. So basically, when you turn this trimmer all the way to the maximum, which will give a time constant of 10 milliseconds. Like after 10 milliseconds, a square wave input will reach, I think like something 60%, around 60% of the voltage. So that gives you an intuitive and quantitative idea about like what is the strength of filtering. And then the smaller the resistance, the shorter the time constant in a linear fashion. Basically, if you turn it all the way to the middle, and then that's 5 millisecond time constant instead of 10. Okay, so lastly, related to the previous topic, when you really don't need the galvanic isolation, for example, when you do imaging, you can use something extremely simple, which is the Teensy built-in capacitive contact detection capability. And I've posted a link about like the tutorial. I mean, it's really a minimal tutorial because that's a really simple thing to do. And here I'm just showing how you do that. So in this video, the content creator is basically hooking up apples to the Teensy, and it seems like he's using Teensy 3.6. And you see, I'll just pause here because you see it uses a single wire, so there's no circuit. Right? In circuit means you have a loop, right? It's going out and going back in from the ground. But here, each apple only takes a single wire to a pin, and then and he just uses a super simple code to. And here, so he's tapping the two, contacting two apples, and then the capacitive contact detection circuit that's built into the Teensy chip automatically figure out like how much capacitance has changed for this external object. So when we are touching it, the object going to merge together with our body, so then the capacitance increases dramatically. And then, and otherwise it will decrease. It will be very small because that will be just the surface determined by the surface area of the apple. And then by detecting this kind of changes in capacitance, it's very easy to detect the contact. So in fact, like capacitive contact detection is a pretty popular method for leak detection. And the reason many people cannot do that is because, like detecting capacitance requires sending out a kind of very high frequency TTLs to the subject or to the object as the testing signal. And then that is basically not compatible with electrophysiology. Okay, we are getting close to the end. Wireless communication. So this is a big topic. So today I will only do a demo. So I will do the demo using our familiar example that we talked about previously. Open an example. So the example is the satellite link data. There's the really minimal things we need to change. So there are many serial ports for Teensy, and so we are not using the same serial port that communicating with the computer to communicate wirelessly. So we need to specify which serial port we are using now, and it's very easy. So it's just instead of previously by default we are using serial because it was the default value. We didn't really need to write it out, but this time we are going to use the serial 1 to communicate. And similarly, in the setup, instead of initialize the serial, we are initializing serial 1 port. And then I think that's it. That's the only change we need to make. Now we can minimize or close those, and then bring out our satellite viewer. If you can see from the little window here, so this is the wireless module. And we're going to connect the XBee wireless module to the XBee interface on the satellite board. So, and this is the satellite side. And we also need to connect another XBee module to the computer. And here I just have a USB adapter into it. And then, so you can see my computer chassis over there. Just plugging it in to my computer. Just like a Arduino board, when you connect it to a computer, it's gonna take a so-called COM port. Since the Teensy is a different device from the XBee receiver I just plugged into the computer, so they will have different COM port. So, but yesterday when I was testing this for this demo, I've already know it's the COM port 7. So, but let me just still show you the configuration. And there's really nothing to show you about because it's the same as the configuration we did before. So general, standalone, or you can use a server if it is a server, and then nothing about UDP/IP and serial. We selected COM7 with the correct baud rate, but here is something important. So we are still using transparent. XBee API is another communication mode that's available for the ZigBee for the XBee module. But here I configured the modules in something called transparent mode, which is the same as just a typical serial communication. It's basically a wire replacement solution. And then we can enable this and show a window. And I hope you can see that the LED on and off is working now. In the camera view, I'm showing the LED blinking, and here just to show that we can actually wire. Okay, so but you may say, okay, so you are still having a wire here, like connect to it, but here I'm just showing you that without connecting to the computer, but we still need to power it up, right? So here I have an external like cell phone kind of power bank, and which only provides power to this circuit board. And if you look at my desktop, the data is still coming. So this thing that right now is really wireless. We can actually do everything we have done before. We can say on, off, duration. So right now is 1 second on, 1 second off, and we can do it like 200 milliseconds on and 200 milliseconds off. And you see it's doing as what we expected. All right, so that's just a simple demonstration, and you can imagine. I'll stop this. Yeah, and you can imagine we can just hook up this little device in a training box or in a rig, and we can basically wirelessly communicate and log data and send command about the behavior. What I just demonstrated is called the transparent mode. But what's really powerful about the XBee is API mode, which is a little bit too advanced for today. But I think the XBee has become less popular as the Wi-Fi solutions has become more flexible. So then in the future, if you are interested and want to have fun, then you can play with the ESP8266 Wi-Fi module and see how to connect your computer with the board using the Wi-Fi in the room. Okay, so far I have kept the Teensy board on the satellite shield, but you really don't need to have this board on this shield in order to use this shield. You don't need to have anything in here, and then you just like power it up using like maybe the 5-volt power supply, and then you can use jumper wires to connect some external signals. For example, it can be from B control and to like the inner, or not inner, sorry, to the outer row of the socket, connecting something directly to the driver controlling pins, or to the contact detection pins, or to the serial port pins that you can use something else like to directly communicate with the wireless modules or peripheries and so forth. So yeah, it's like we plugged it in simply for convenience, but you certainly don't have to do that. You can use this board in a standalone fashion. In fact, in earlier version of the satellite shield, where I didn't kind of provide this kind of flexible selection of voltages, so when I needed to use like 2 or 3 different voltages, I actually have one like this and a second satellite board next to it, but operating at a different voltage level or different reference level. So yeah, this can be very flexible. Yeah, this is how to use the satellite board. What if I want to make a satellite board? First is, where are the design files? Again, we go to the GitHub, go to satellite repository, and here we have satellite shield. And right now we are using satellite's PCB version 2.0. The 2 files here, the .board file and .schematic file, are the design files. They use that, like, like it's a project file. So this is equivalent. If we use SolidWorks for 3D printing, it's like the SolidWorks parts files, SolidWorks assembly files, the design files. But when you finish designing, then you generate something called a Gerber files. And so this is the complete set of these files for manufacturing. And here, the zip file is basically just a package of this folder. If you want to start like modifying my circuits, like like replacing the signal detection circuits, or you think the breadboard area in the satellite board is such a waste of space, every time if you want to build some external circuits, you have to do kind of hard soldering work here, and you may actually want to just design to modify this area so you can have some convenient connections already here, and every time you want to build a board, you just need to you just solder the part as the rest, and without the need to kind of painstakingly route the wires. So then in that case, you may want to learn a little bit of how to design and make your own PCBs with Eagle, and this is the book I recommended. And then I learned everything about PCB design from this book. So, okay, that's a digression. But going back, once we have the Gerber file and we go to this website, the seedstudio.com, their PCB manufacturing service is called Fusion. I don't know why, but here we can say order now, and on the top is asks us to add Gerber files, and here like we just upload the zip files I just showed you, and here are a bunch of selections. The default for this one is fine, and then we have our layer is 2 layers, and the PCB dimension is really just for them to calculate the price, and the dimension for our board is about 50 millimeters times 100 millimeters, and you can order 10, 15, 20 boards. Let's try 10. So you see the prices updated here in real time. And I think the most important spec is the PCB color, and green is the kind of default color, which is kind of lame. And we want a cool color, and black or blue. And so for surface finish, are the material used for like this kind of pens, and we want to have a lead-free pen, unless you really prefer the one with the lead to make the soldering slightly easier. But I always use the lead-free, and there isn't really anything else to specify. And look at the price; it's $13. The company is in China, and so I think the cost is mainly the shipping, and the time is also actually pretty fast, pretty quick. So this is how we order that. And then the last thing I will demonstrate is the list of components and how to do the soldering of this board. But I'm not going to demonstrate that right now. Yeah, so I have already made a video tutorial for this, and then I will post that. Well, I will append that video tutorial to the end of this recording. So that has a very detailed demonstration from an empty board to this finished design, and all the tiny things, caveats, cautions, and then tricks, tips, and you can find everything over there. So this is 1000 times 10, no, times 100. So this is a 10 kilo resistor. So this is a 1K resistor. All right, flip to the back side. Next, we are going to solder these ICs. So make sure the notch is facing the side indicated by this notch. In this case, you see a dot labeled on the IC, and as well as the dot on the print of the board. And we make sure the two dots are pointing to the same side. So to avoid overheating, we solder this pin and then go to a pin that's not in the vicinity of that pin, and maybe I will solder this next, and that next, and that next, and then go around back to solder this, and so forth and so on, giving each pin some time to cool down, each area sometimes to cool down. And I can go to another IC, like soldering this and soldering that. Next is solder the capacitors. Well, it seems that the two little capacitors are about the same height as those resistors, or somewhat in between those resistors and the ICs. So make sure the opening of these terminal blocks are facing outside, right? You see, this is the openings or the sockets, and this is the back side. The back side is facing inward to the board, and the sockets are facing outward. Same for this, same for that, same for that, all facing outwards. Alright, it's time to flip it. How are we going to flip it? Well, we just use another board, put it on top, and flip. But what I will do first is to anchor each component. For example, to anchor this block terminal, and we just need to solder two of the pins. And this block terminal is not going to move anymore. So anchored, 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 not anchored, not anchored, not yet, not yet. Let's do these first though. So these are transistors and they're pretty delicate, so solder them for as short time as possible. Yeah, that's good enough. And I will do the other one first. Add a little solder to the tip. Yes, I just made sure I have soldered everybody, and this will be the last one. So these two single row female receptacles is going to connect with the 2 rows of male pins from Teensy. And to make sure they kind of mate with each other properly or in an optimal way, so we'll actually just use a Teensy board for that. Well, I have a Teensy board over there, but here I just want to solder a new one. So, and to make sure we solder 2 nice rows of male pins onto this Teensy 3.5, we will use a breadboard to make sure the positioning is correct. So we will need these many pins over here. And same on the other side. So I think plugging them into a breadboard is actually necessary. It's more than just making sure they are positioned very well, but also the sockets inside this breadboard will dissipate the excessive heat. Alright. So be very careful when soldering this, because we are going to get pretty close to other components, and we don't want to damage those components or kind of melt the solder of the other components. We'll begin from the middle, because the middle pins sort of anchor the whole board this way, and I'll do the other side, pressing down a little bit and use the fingers to press down. Yeah, they look good. Now I'll do the rest of them. Again, first to anchor this one, solder this pin and hold it down, and the one opposite to it, hold it down. Yeah, so this secures its position. Yeah, let's solder another pair first before detaching the Teensy. Well, actually, let's just solder everybody. So we can use Teensy as a heatsink to dissipate the excessive heat. do the potentiometers first. So they are 100 kilo ohm potentiometers. These capacitors are polarized, so the longer legs are positive and the shorter legs are negative. So the longer legs should go into the hole with the plus sign and the other the negative sign. Well, it's a little bit unstable, so what I'm gonna do is to find another capacitor like this and insert it in insert it over here. Yeah, but remember, don't accidentally solder that. When we actually use this board, we will need several jumpers. First, to connect and select these power options, both here or here and or here, as well as bridging some pins from the row at the inside to the row on the outside, like same for the other side. And those connect, as I will explain in the tutorial, those will connect those pins to either the Standalone transistors for power output, or to the contact detector circuits. And to do that, it's actually very simple. First, for these male pins, we simply use these jumper hats to bridge either these two pins or that two pins. And by default, we'll just bridge the 5-volt power supply to the driver power. Same for the other side. Alright, however, these are female receptacles, so we need male headers, and I don't have male headers, but I can make some. So these are pins with longer legs. So on the top side, that's the normal length for a male pin, but at the lower side, and this is the length of a male pin plus the thickness of a PCB board. But here we'll use this in combination with the jumper hat and turn it into a male jumpers. So you see, by combining the two, and we can just bridge any pins across the two rows. I will make a few because we're going to use a lot of the peripheries. Here I'm just randomly plugging some. Alright, now this thing is ready to be used in a rig.